Back. So reminder, your next homework assignment's due on Wednesday. What we're going to do mainly today is talk about root finding for functions of one variable. So this is perhaps one of the most classic topics in numerical analysis. And I'm going to do two things. Well, before I do that, I'm going to make a few remarks about the speed of multiplication in various fields using a different sort of benchmark. So I'll use a benchmark which is a siphoned cdef for loop, and this will help avoid a lot of overhead that comes up in trying to benchmark the speed of multiplication. And it'll give us a good sense of how various types behave when you do arithmetic with them, where it gets rid of a lot of Python overhead, etc. So right here, for example, when you multiply these in Python, there's extra work because A has to get looked up in the module dictionary and so on. Whereas in Python, that doesn't have to happen. So by using a Python loop to do the benchmark, we'll get a better sense of what the times are like. And we'll see that, in fact, interval arithmetic is significantly slower than floating point arithmetic, than normal double precision arithmetic. So I'll talk about that. Then I'll talk about something called fast float, which is something that takes an algebraic or really a symbolic expression like sine of x plus cosine of x squared divided by square root of x, for example, and turns it into an object that can be evaluated very, very efficiently. And this is a system that Robert Bradshaw in the back of the room wrote. And I'll give you some demos of how it speeds things up, and then he'll make a few comments about how it's actually implemented. And it's extremely useful, and often the result is faster than we could possibly get just by playing around with pure Python functions. So it's quite impressive. And so I'll talk about that, and then I'll talk about the bisection method, which is probably one of the simplest imaginable methods for finding roots of a polynomial on an interval, or not a polynomial, a general function actually. So you have a continuous function on an interval, and you know by the intermediate value theorem, say, that it has to have a root somewhere on that interval. The bisection method is a very simple way of kind of converging in on one of those roots. So I'll show you an implementation of it, describe what it is, and discuss I'll discuss various aspects of how it's implemented in Sage. Really to give you a sense of, and you'll learn more than just about the bisection method from this. Then I'll talk a little bit about Newton's method. It's another method for finding a root of a polynomial, or more generally any function that's continuous and differentiable on an interval. Newton's method is a little different than bisection because you start with an initial guess for a root, and then you do an iterative procedure. And if things are really favorable at each iteration, you get much, much closer to the root. Though, of course, things can go terribly wrong with Newton's method if you don't make a good guess initially. So this is what I'll talk about today. Before I get started, any questions or comments about anything in the class? Okay. Oh, one other thing, my office hours will end a little early today because I have to go to a general's exam that starts at 3 o'clock. So I'll only be in my office hours until about 2:50. Okay, first, notice, by the way, that all of the output is missing. There's no output at all. That's because in the next version of Sage, there's a handy feature called delete all output, which just removes all the output, which is nice. So here's an example where we do 1 million times multiplying multiplying the real double element that's pi, double precision. And you'll see that it takes 0.05 seconds. Here's doing the same thing with Python floats, which takes 0.04 seconds. Just to make sure that this isn't somehow optimizing, the compiler isn't somehow optimizing the entire loop away, I'll do it with 10 to the 7th, so you can see that it does take longer. So, here's an example with complex double field, and an example with Python complexes. The fact that this is 0.17 versus Python complexes being 0.06 is a little worrisome. I would think these should be very similar. So somebody might want to look into that. There's something non-optimal about that, how that's implemented, I guess. Okay, So real interval field. So here, this is very interesting. So what we're going to do is take the real interval field and then benchmark that same thing. So we're doing 1,000,000 squarings, or actually multiplications of something by itself, in the real interval field. And you'll notice the time, once you get rid of all kinds of other overhead that you have in pure Python, the time is actually pretty big compared to the time of doing it with doubles. So it's over a factor of 10. It's almost a 15-fold difference. So before, that was really masked by additional overhead we had in doing a pure Python for loop. But when you get rid of all that overhead, there is a significant difference. So if you were to pretty tightly code things and use double precision versus using intervals, you should expect, if you've done lots of tight coding, that there should be a difference in speed around a factor of 10, at least. Okay? So keep that in mind. That may be perfectly reasonable given your goal, or it may be completely unreasonable. It really depends. But you should expect something like that. One thing, the way intervals are implemented under the hood is this MPFR library, multi-precision floating reals, that allows you arbitrary precision floating point arithmetic that Paul Zimmerman wrote. So real intervals are pairs of those things. And those things are, though fast, they're much slower than double precision. Let's do the benchmark with just this. So you can see that doing arithmetic with real intervals is about twice as costly as doing arithmetic with just a single real, but where this is a MPFR real number. And this is nearly 10 times slower than a double. So you have a factor of 10 difference between the two. You might ask, why would you ever use these? The reason you would want to use this, one, is that you can do much higher precision. You can say, I'd like to keep track of 20,000 bits of precision, and it will just work, and you don't change anything else in your code. Whereas with doubles, you're stuck with double precision. The other thing is that the exponent, in other words, the range of values you can consider here, can be arbitrarily large. Same with real interval field. Whereas with double precision, you get at most about 10 raised to the power of 308. So if you have a very, very large number with thousands and thousands of digits, if you were to write it out, then with RR you can keep track of that, whereas with RDF you can't. Okay? So there's a much wider range of values with RR, which is this MPFR-based thing. So it's slower, but it has several advantages. So you lose a factor of 10 in speed with this, but you have a much wider range of values. You can do arbitrary precision, in which case you'd lose even more than a factor of 10. If you switch to 1,000 bits, you'd start losing a much bigger factor, of course, because you're computing a lot more at each step. A third advantage, by the way, is that the behavior of RR is identical on any machine, whereas with RDF, it can depend on the different machine that you're using. So there you are. And just for fun, here's an example where we do the same benchmark, but with high precision, say 1,000 bits of precision. And it's significantly slower, so 1.83 seconds instead of 0.39. Because at each time we do the arithmetic, we're squaring the number and we're keeping track of 1,000 bits of precision instead of only 53 bits, which is all you keep track of with a double. Also with intervals, you can raise the precision if you want, and it takes correspondingly longer. Oh, and by the way, remember there's quad doubles. So one of these is 4 doubles. And there you are. So you can see that also takes extra time, in fact 10 times longer in this benchmark compared to doing arithmetic with just doubles. And I mean, part of the reason is that, for example, doubles are implemented in hardware, whereas quad doubles implemented in software on top of something implemented in hardware. So if people are making video games and doing computer graphics cared a huge amount about quad double, this would probably be a bit faster. Okay, so now I'll talk about root finding, but before I do that, I'm going to talk about this fast float evaluation thing. So first, it works on a couple of different types of objects in Sage, but it particularly will work on most things in the symbolic ring. So that's when you make a symbolic variable, and then you make some sort of calculus-like expression using that symbolic variable. But if you have such a thing, so here's an example where I take E, just some number, and I can evaluate F at it. Now let's see how long it takes to evaluate this a bunch of times. So it takes 406 microseconds to do that evaluation, which doesn't sound too bad. But look at the difference here. So if you do fast float, you get back an object that's constructed out of F, and it's a little bit faster. Doing exactly the same evaluation is literally, if you look at it, a lot. I mean, that's a lot faster. That's 1,000 times faster. Microseconds versus nanoseconds. What's going on here, I think, is it's calling maxima every single time, right? In this. So what happens behind the scenes here is when you do f of a for that, it sends to maxima the statement, please evaluate this function in maxima. And that just goes over a tty. And then in maxima, it evaluates it and gets some number back. Then that number comes back from maxima in decimal, and Sage parses the result and creates a symbolic thing out of it, and then it creates a symbolic thing out of that. And then that could get turned into actually, I don't know if it gives a symbolic or a float back. I should check. Because the nice thing is that the fast float gives back, whoops, that's not what I meant to do. Let me see what it does. I don't remember. Yeah, it gives back a symbolic constant. So really the equivalent thing, if we wanted to benchmark this, would be float of that, which is an additional step. Because that's usually what you end up doing when you're, say, graphing a function. So you're computing float of it and so on. So, I mean, on the one hand, it's pretty miraculous and amazing that it takes only 412 microseconds to evaluate f at a point, given that it's literally calling another computer algebra system. That computer algebra system is evaluating the function, giving the result back. Everything's going back and forth over a tty, and it's going in base 10 ASCII. And you're doing all this parsing. So it's pretty good that it's that fast. On the other hand, using fast float, which Robert wrote, it's 1,000 times faster. So that's pretty impressive. And just to give you another example. So here's a function of two variables. And I'm going to time, remember again, a is just e as a float. I'm going to time evaluating that function of two variables at a comma a. And it's going to do it 60 or so times and tell us how much it takes per time, per evaluation. So it's a function of two variables. And then we'll see how good fast float is in a minute. While we wait, maybe Robert can make some remarks about what fast, you can come up here if you want, whatever.
Okay, sure. So,
like, what the heck is fast float doing behind the scenes?
Yeah. So what fast float is doing is it's taking it's taking whatever expression you have, and it says, well, what arithmetic do I need to evaluate this? So if I have something like, and then if I do a plus b like this, what it does is it says, well, what I'm really doing here is I'm taking something, I'm adding, and then I'm multiplying in something else. And so in the other sense of doing it, what it does is it has to say, oh, I have a symbolic expression here. What kind of a symbolic expression is it? Oh, it's an addition one. How do I get the first argument? How do I get the second argument? How do I add them? And so on. And there's a lot of extra things to figure out. So what it does is it converts it into a kind of, I don't know if you've ever used the HP calculators, but it's the reverse Polish notation, where it's like a, b plus c times. And then there's a stack. And so what this does is it puts a on the stack, and it puts b on the stack. Then it says, oh, I've got a plus. So what I do is I take these two things, and I replace them with a plus b, but evaluates this just using the hardware, using the fact that they're just doubles. And then I put c on the stack, and then I see the multiply.
So it's very cache friendly.
Yeah, it's very cache friendly, and these aren't Python objects. It just has a pointer into chunks of 64 bits that represent doubles on your machine. And then this right here, when you're done with it, it just pulls the top thing off the stack, and that's exactly what you have.
And then you have a bunch of special code for things like sine and cosine.
Yeah.
I mean, maybe you could say something like, what if it were a sine of c?
Yeah, for sine and cosine, what it does is there's a c function that will take the sine of something, that ships with standard c. And so it actually just takes a pointer to that function. And then when it hits the sine, there's a special token here called function, and it says, oh, then I take this address that's sticking out here must point to a function. And so I call whatever function is pointing, this thing is pointing to. And it's a C call, and that returns, say, the cosine of the variable. And then the other thing is, if you can also point to a Python function, so you can have any Python thing in your fast float. And of course, then it will call out to Python and it won't necessarily be fast. But there's not just a limited range of things that can be in your fast float. But if there's a C equivalent, then it'll stick the C equivalent here. So it's really fast. So you guys probably done running by now?
Yep, 61 seconds. 3 seconds per loop. Now you could try the fast float version, which takes. It's really annoying. Okay, so 61 seconds, and now I make a fast float. Here's how fast float is in the same thing. So without using fast float, 3 seconds. Using fast float, 589 nanoseconds per loop. So fast float is a lot faster. Yeah?
And you'll notice that that's not very much slower than the previous one.
Right.
So, you know,
very
several
well.
hundred nanoseconds of that were overhead and calling fast float, not fast float itself.
So a lot of the motivation for this was drawing 3D plots, where what was happening is it was taking this sort of time to draw, to evaluate the function at some big mesh and draw a 3D plot. So it would take forever to draw a nice 3D plot to high precision. So then Robert implemented fast float, which for a while what people were trying to do would be to just take their symbolic function, maybe rewrite it to be a pure Python function. That helped some, but it still wasn't. It was very inconvenient, ugly, and fast float's actually a lot faster than that even, which is pretty amazing. So now what happens is you can evaluate a function on function of 2 variables on some mesh with lots and lots and lots of points to high precision, and just the additional drawing steps after that end up dominating the time when you're trying 3D plots or doing implicit plots. Like if you're going to do an implicit plot of a function, you need to evaluate lots of points to figure out where the function is 0. So that's a really useful thing to know about. And in this particular example, it's looks like it was this time 3.03 seconds versus 589 nanoseconds. So 5 million times faster. So fast float was pretty new 2 months ago, I think. It should probably be the case that when you try to evaluate f the first time, it just does the fast float, creates that object, caches it, and then uses that for evaluation in the future. Don't you think? Any comments?
Yeah, that makes sense.
Yeah, I mean, it's something we didn't want to do initially because fast float was extremely new recently, but now that we've used it for a while, it works really well. It's good. A lot of functions like plotting and so on will just implicitly check to see if there's a fast float object. In other words, they'll check to see if fast float works for your input, and if so, then they'll use that instead. So you don't have to worry about calling fast float explicitly in most cases. But it could make a massive difference if you're calling. So SciPy is this huge library that knows nothing about Sage or fast float or any of that. If you passed in this function f up here directly to SciPy to do some sort of interesting root finding of a 2-variable function, it would sit there and it would just be evaluating it as it is, and it would be a million times slower than if you pass in the fast float version of the same function. So you can see that this is it's an issue, and it's really an issue about integration of different systems and so on. But you can see how somebody could be deeply misled about the speed of Sage based on not knowing about this fast float thing. Where, I mean, on the one hand, Sage is slower than everything else, but on the other hand, Sage is faster than everything else. It's kind of funny. When we were at the conference in Sage Days 8, which was at the NThought in Texas, so this was a couple of months ago, we showed them fast float, and they said, well, you should be using numx, which is it's basically our version of something that does that. But it turns out fast float, on their first benchmark they tried seriously, was still 20 times faster than their numx thing. So fast float's pretty good for what it does. And I think it needs to be improved. Okay, so now I'm going to finally talk about a little bit of numerical analysis. Jim, since you're an actual numerical analysis type person, if you have any comments at any point, feel free to interrupt and make them. Okay? So here's an example of a function on an interval with the property that the value at one endpoint has a different sign than the value at the other endpoint. So a theorem in calculus called the intermediate value theorem tells you that that value 0 will be taken on by the function f. And a basic question in numerical computation or some scientific computation is to find, to some precision, that value right there. Okay? It's a basic question. It generalizes, of course, to functions with several variables, and there often you're interested in things like finding a local maximum or a local minimum, which when your function is differentiable, you can often reduce to the problem of finding a zero. So here's one of the sort of simplest ideas imaginable for finding that zero. It's sort of a divide and conquer approach. So what you do is you take an interval which definitely contains the zero, and you chop it in half, and you look on each side, and on one of the two sides, let's just say the left or the right-hand side, the sign still switches. Or right where you chopped, maybe the thing is zero, in which case you're done. So if the sign switches on the left-hand side, take that subinterval. The sign switches on the right-hand side, take that subinterval. Just keep doing that. And eventually you're going to get, every time you do this, the size of the interval is half as big. So you're going to get a smaller and smaller interval. And on every single interval that you consider, your function is going to vanish somewhere. So after a while, your function is going to be really small at the middle of the interval. And there, it's a completely straightforward way to find a root of a continuous function on an interval. Of course, if you're really clever, you can cause all kinds of trouble, but anyways. So that's the algorithm. It's just the bisection algorithm. I've just written it down here. And what I'm going to do is implement it in pure Python and Sage right here, and then show you some examples. And then I'll discuss how to find the SciPy implementation of the same algorithm, and then we'll compare some things and so on. Okay? So it's a pretty simple, straightforward idea. You simply divide and conquer. You just keep looking, dividing the search space up in half at each step until you find something that is close to being a root. You don't know how close the middle of the interval is to being a root, but you know that if you know what you get if you evaluate the function at the middle. So you have to decide when you're going to terminate the algorithm. And the way I set it up here, you terminate it when f evaluated on the point in the middle is close to zero, is within epsilon of zero. So it's really not so much that if your function f were less than epsilon everywhere, then you just take any point to be a zero. So you have to know something about your function, or it could be kind of silly. So again, the termination condition is always a big deal with this. So the termination condition I'm making here, which is usually good, is simply that f of the midpoint of the interval is smaller than epsilon in absolute value. And then you just choose the epsilon as input to the algorithm. Okay, so let's just try it out. First, here's the implementation. So I define a function called bisect method. Takes as input a Python function, well, actually a Python object, two real numbers, a and b, and an epsilon. It first tries to turn it tries to get a fast flow analog of the function if possible, and if not, just forget about it. We'll just use the function that was passed in. So this is a sort of code that is at the top of a lot of the plotting functions in Sage. So it tries to get a fast float version, and that way in the rest of the algorithm it'll use the fast float version of f, which is much, much faster, as you've seen. So what it does is it's going to record the intervals kind of for illustrative purposes. This is mainly for illustrative purposes. And then forever, it does the following. It evaluates the function. I've made no attempt to optimize anything. I'll have a more optimized version later. It figures out the midpoint of the interval, evaluates the function at both endpoints and at the midpoint. And if at the midpoint it's less than epsilon, you're done, you return. If the left-hand interval has a sign change, so the value at the beginning and the end of the interval is negative, then we take that one. If the right-hand one has a sign change, we take that one. Otherwise, we just raise an arrow. So you could, of course, come up with some way of throwing this off, but this is mainly for illustrative purposes. And then we record the interval. So that's it. That's all I've implemented. It's just supposed to be a straightforward way for a reasonably well-behaved function to find a root to some precision. And now I'll make an interactive version of it so you can play around with it. So here it is. What you do is you type in a function. I've typed in cosine of x minus x. You type in the left and right endpoints of the interval that you want to work on. I started with 0 to 1. And then you choose an epsilon that's a tolerance. And what it's going to do is keep bisecting until it finds a interval where right at the middle of the interval, the value has a property that f evaluated at that root is less than epsilon. Notice that that value in absolute value is less than 0.01. Sorry, 0.001. And the picture shows a plot of f along with the first interval that got chosen, then the second interval that got chosen, and the third interval, and so on, all the way up until it was finished right here. So now we can just make up any function at all, plug it in, and see what happens. So that was cos x minus x, maybe cos x minus sine x. Try that. And what happens is, again, you see that we're going to find some root on the interval from 0 to 1, and it chooses the right hand, then left-hand subinterval, and then the left-hand one and the left-hand one. And it kind of zeroes in on this root right here pretty quickly.
Did you have a test in the beginning to check to see that the values at opposite ends were?
It doesn't actually. It only tests that the first time through.
Yeah, but I mean,
yeah.
If it tested and kick it back and say.
Well, I'll show you what happens. Yeah, it'll fail. So if I do 0 to 0.5, it'll draw the function for you, but then it says they have to have opposite sign. So that way you can see what the function looks like, which will give you an idea of how you need to change things. So here's another example where finding the root right here. Notice in this example there's two different roots, but it finds this one because it just chooses the left interval. So if you didn't have a nice picture of your function or understand it, you're not really guaranteed too much about which side it's going to choose. And if you can make the epsilon smaller, and then there'll be more iterations. So this one took 30 iterations, as you can see. And there it found a c, so that when you evaluate, you get something that's less than an absolute value, 10 to the minus 10. So it's pretty straightforward, and it gets the job done. Any questions? But it's certainly not the ultimate root finding method. For example, it's kind of stupid if you give it a line that doesn't really say x minus 0.5 from 0 to 1. Actually, that's quite bad. It's from 0 to 3. So like it takes 34 iterations to find the zero of a line. You can find the zero of a line a lot more quickly than that. So it just doesn't take into account in any clever way anything really special about the function or its derivative or anything. So that's really the weakness of this method. It's very, very general. It doesn't use the function's differentiable or anything. On the other hand, it's hard to really confuse it because it always, no matter what happens, the interval that you're on shrinks by a factor of 2 each time, so you will get something. Okay, so now I'm going to show you something called scipy.optimize. This is something included in every copy of Sage for free. You don't have to buy the optimization toolkit or something. And if you do help of it, you'll see some of its functionality. Wow, that's one big output. I think it's taking a long time to render because it's a... Okay, help scipy to optimize was a bad idea because it's absolutely massive. I think Firefox is not happy rendering that. Sorry. I spent the weekend improving the notebook, and one of the things I did was make the output of help with something look a lot nicer, but I also made it so it never truncates it. So I guess that's not so good if the output's huge. I have to log in. Yeah, so good old Firefox hanging, of course. Okay, so I just switched to Safari, which does better. So here's scipy.optimize, and there's the output of help of scipy.optimize. You can see that basically it has a lot of different optimization routines. Could you actually close that window? Thank you. So it has really a bunch of different things. It's trained, optimized, kind of every optimization thing you can think of possibly is in here. In particular, this bisect functions there, right here. Thank you. It's a pain in the butt to close that one down. Yeah, they get to pull. Yeah. Right. There's really a lot here, as you can see. So let's try it out. Since this is so big, I better delete it from the, or actually hide it, I guess. Well, it's probably easier to do SciPy. Okay, so let's look at just the bisect version. So this is a function bisect, which is in SciPy.optimize, where SciPy.optimize has a lot of different things in it. And this is an implementation of, done by people who have thought through some of the issues. And it takes as input a function, something that's callable, an a and a b. And I don't know what args does exactly to read this. I guess extra functions that, or extra arguments that you plug into the rest of the function, and a tolerance, and some other tolerance, and so on and so on and so on. So there are a whole bunch of different inputs, and there's different things that control how much output you get, so how much information about what happened during the bisection process, and so on. And then a list of other related functions that you might want to see. Now let's just try it out. So we'll make exactly the same function, and then call SciPy optimize.bisect. So we get 0.739. And I'll just compare that with what we implemented above, which was bisect method f. Actually, we don't need to do that. 0, 1. And that was the one I implemented above, which also returned all of the intervals in the bisection process. And you can see that if I make the tolerance big enough, I get something that's pretty close to the root that SciPy finds. Okay? Now the next thing I'm going to show you is I'm going to find the source code for SciPy.optimize.bisect. If you just look at it using double question mark, you don't get very far. You'll find that it has a docstring, a Python function that's in a certain file that you can track down. And then the actual implementation just calls into a C module called _zeros and calls bisect in there. If you look a little bit closer at the SciPy source code, which you can extract, then you'll find, by the way, let's compare my implementation of bisect to the SciPy one. So the SciPy one takes 15 microseconds, and mine takes 520 microseconds. So you'll see that theirs is vastly faster than mine. So looking in the SciPy source code, which comes with the source tarball for Sage. If you look inside at that file, which is included in the SciPy source code, then you'll find this, something written by somebody named Charles Harris. There's email address there, and then there's a C function which actually implements bisect. And here it is. So this is a C implementation. There's a book called Numerical Recipes in C, and you'll find tons and tons of implementations of basic functions like this that are important in numerical analysis. And I don't know whether this follows that one closely or not, but if you really, really like to see massive numbers of pages of implementations like this, you can look at that book. But here's the implementation. And you can see there are a few things that make it faster than the one that I showed you. In particular, he only evaluates the function once. It's completely wasteful to evaluate the function at both sides and the middle, because from the last evaluation, you already had at least one of those endpoints. So there's definitely some waste in the way I implemented things, etc. Also, of course, this is written in C, which gives you a nice speed up as well. I was a little surprised, actually, to find that it's written in C. I expected Fortran code, since a lot of SciPy is written in Fortran. But it turns out this isn't C. So just for fun, I wrote bisect in Python. So all I did was declare data types and then slightly change the algorithm I had above to avoid redundant evaluations. So let's see how this does. So now I'm going to time the SciPy version. Well, first actually I used both of them. And you can see that what I did was with SciPy I told it to iterate no more than 20 times because I noticed that in fact it took 20 times of iteration through this to do that particular example. So now let's benchmark or time the two to see if the Python version of bisect is at all comparable to the SciPy pure C version. And it turns out that it is. In SciPy, for doing this particular example, with at most 20 iterations, takes 11.6 microseconds. The pure Python one takes 654, so that's 50 times slower. But the Python version actually takes 4.83 microseconds, so it's over twice as fast as the pure C version that's in SciPy for some reason. One thing to keep in mind, the one in SciPy is maybe is a slightly different algorithm. So maybe its termination condition slightly different or something. So it may not be a completely comparable benchmark.
We have more tests in it too.
Yeah.
Mike?
Yeah, so this might be partly an illustration of how you could implement certain numerical methods in a way that runs quickly, but in real-world applications could be bad. In fact, if you sit down, I don't know from personal experience, but I've read in many places that if you sit down and just decide you're going to implement some huge framework, lots of algorithms for doing numerical computation from scratch yourself, the odds that the result are not going to contain tons of subtle numerical errors are huge. I mean, it's going to be a big problem. And that's why if you look at the actual numerical computation libraries that are out there, like GSL, the GNU Scientific Library, and SciPy itself, and of course MATLAB, a lot of the code for doing numerical root finding and so on is pretty old in all of those systems. And it's old for a reason, because people don't want to tweak it and write new things, because they'll just turn out to be wrong. So maybe I'm just illustrating that here. On the other hand, suppose that you had a function where you knew that the bisection method would be you have, say, some class of functions that you understand pretty well, and you know that the bisection method is going to be a kind of good thing to use. Don't naively think that just calling SciPy's optimized bisect is going to be the right thing to do. It may be that those extra tests are not necessary for the particular function you're looking at. It may be that you can, in a few minutes using Python, code out something that's substantially better for the class of functions you're looking at. So don't just naively believe that because it's in SciPy, it's significantly better than what you might do yourself. As you can see here, this is almost 3 times faster. And there are lots of functions for which my bisect is going to be just fine. And of course, if you code it up yourself, then you have the advantage that you can tweak everything. So it's always a trade-off. All right, here's another example, Newton's method. So I need to evaluate this. Okay. So this is another numerical method for finding a root of a polynomial. And it's very clever because it takes advantage of not just the function, but the derivative of the function. So it takes advantage somehow of the shape of the function. And in particular, for, say, a linear function, it converges very quickly to give you the answer. And for a lot of everyday functions, it has quadratic convergence. Namely, if you choose, what you do is you choose some root, and then you run this procedure. No, sorry, you choose some approximation to a root, which could be a terrible approximation. You run this procedure, and every time you iterate it, after a while at least, it doubles the number of digits that are correct. So very, very quickly gives you more and more digits of a root. Of course, you could choose a function where, and a starting value which is stupid, and for which you never get anything improved. So it doesn't always work beautifully. But under certain hypotheses, very often it gives you excellent convergence, especially if the function does not have a 0 of order 2 at the point where you want to find a 0. Okay, so here's the algorithm. It's just a really simple idea that's, I guess, due to Newton and Raphson, and goes back, of course, hundreds of years. What you do is you take your function, f of x, and as I've drawn here, you take a point where you'd like to find a root somewhere near that point. And what you do is you just draw a line that's tangent to your function at that point. And then you find where that line intersects the x-axis, and then you make that your next approximation for the root. So you do the same thing again, but now you start right there. And if you iterate this procedure, you'll get closer and closer to a root, unless you're in some really bad case where you won't. So, so formally, it's really, really simple. The equation of the tangent line to the graph of a function, a differentiable function f of x at the point c, comma f of c, is just what's given right there. It's y equals f of c plus f prime of c times x minus c. And you can easily see that that's the graph of a line. And you can also easily see it goes to the point c, comma f of c. Because if you just plug in x equal to c, you get 0 right there in that factor, and you get f of c for the value of y. And you can also see easily, because it's, if you think of this as being in kind of slope-intercept form, the coefficient of x gives the slope, which I wrote the slope, but I meant slope right there, of f prime of c. So this has slope f prime of c, which is, of course, the slope at that point. So here's what you do. You approximate f by that line, then pretending that your function is that line, you find the root, which is really easy, because it's easy to find a root of a linear function. So you just set y equal to 0, and solve for c. Sorry, you solve for x. Yeah, set y equal to 0 and solve for x, and this is what you get. Which is, if you set y equal to 0, you just have minus f of c equals f prime of c times x minus c. And you're solving for x, so you divide through by f prime, and that gives you this. And then you add c to both sides and you get this. And that's it. That's Newton's method. And I mean, it's really, really powerful. Let's say, actually, once I was on an airplane and this 9-year-old kid really, really desperately wanted to know how to compute square root of 2, who happened to be sitting next to me. So it happened. And he just had no idea how to compute square root of 2. So I said, hey, take the function f of x equals x squared minus 2, and then try to find a root to it, or a root of it. And oh, by the way, here's an easy idea for finding a root of a function. So here's a function, and there's a way to find a root given something that's close to a root that converges pretty quickly. So I just wrote down this function, wrote down this little formula right here, and said all you have to do is iterate this formula, and every time you do it, you'll double the number of digits of square root of 2 that you're getting. And he was very happy about that. So let's try it out. And again, just to summarize the algorithm, you have a function f on some interval, and you want to find a root. So you choose some guess for a root, which you just pull out of thin air, possibly by drawing a graph of your function or something. And then you iterate c equals c minus f of c over f prime of c. So you replace c by c minus f of c divided by f prime. And you just decide that your terminating condition is, say that the absolute value of f of c is less than epsilon. In practice, since there are examples of inputs where the thing will just go on forever and not terminate, it's good to have a specific number of iterations that you'll also stop at. So that's what I do here. So I have a max iteration parameter.
So since the precision doubles, then you can make a pretty good estimate.
Usually it doubles, yeah. Yeah, you're right.
Well, and so,
Yeah, yeah.
So you shouldn't iterate very many times.
Right. Yeah, so you'll know ahead of time. Okay, so now let's try it out. Let's look at the implementation for a little while first. We'll try it out. I'll make this bigger so you can see it. There we go. Okay, so here's my implementation of Newton's method. And so first we try to get fast slope versions of both f and its derivative. Then we, at most max iteration times, just iterate c equals c minus f of c divided by the derivative evaluated at c. I just use the notation g here for the fast flow version. And each time we append the actual iterate, since it's going to be nice when we draw a picture. Okay, so I mean it's really easy to implement Newton's method. It's actually easier than the bisection method to implement. And by the way, I'm not saying this is the best possible way. I'm just saying it's better than the bisection method in a lot of cases. In fact, it's not the best way. And if you were really designing a system for doing numerical computation, you would have this as one of the tools in a vast tool chest, which SciPy Optimize already has. Okay, so there we go. So now we get to try it out. And there it is. You put in your function, x squared minus 2 in this case. We'd like to find a root. So we start out with 0.5. Not a very good guess, but we start with 0.5. You choose a tolerance, and then you iterate. And in 5 iterations, it finds that root right there, 1.4142, etc. And you can see here, what this is doing is it draws a vertical line. I also make the points kind of go down so you can see where they are. But it draws a vertical line where at the ith iterate. So basically, you can see these, and then the rest of the iterations are so small you don't see anymore. I mean, almost every one of these pictures, you'll see 3 or 4 looking different at most. And then each time, since the number of digits is doubling, I mean, you can't see the difference between a number and a number with twice as many digits the same. But let's try it with a smaller tolerance, a much smaller one, e to the minus, or 10 to the power minus 11. And here, there are 7 iterations, and you get this approximation for square root of 2, which when you square it is 0 to 16 decimal digits. And notice that there's the first, I guess the first guess was a half, so that must be right here. And then over here, and then back, and then they're all on top of each other as far as you can tell right here. If we want though, if you make interval really small here, we'll get to see what happens just in a little tiny neighborhood about the root. So here you can see, I'm just drawing a very, very small interval around the root. And you can see again that after the first or second iteration, it looks like they're all on top of each other. And if you look at the actual approximations that are going out here, they're very, very good. By the way, here's what square root of 2 really is. So it's just right on the nose. And it didn't take much work. I mean, even certainly Bernoulli could do that too. And this will work. It doesn't have to be a polynomial. I mean, just anything that's differentiable. So let's try to find a root of that function. Okay, so that function is sine x minus cos x plus x squared. And after a couple of iterations, it finds this root, which is 0.56 right there. Okay. And now, just like before, if we look at scipy.optimize, just use scipy.optimize.tab, you'll find, optimize.tab. You see all these different functions for optimization, and one of them is Newton. And if you look at the help on Newton, you'll see that there's a Newton iteration. And it has various inputs, and it also has a C also, which tells you about similar functions, like n-dimensional root finding, etc. And now let's just try out. So SciPy Optimize works as well. And good to have. Okay, here's what I do. I'm going to implement the Newton iteration, but just defining all the data types in Python, just for fun. And then I time. So by the way, one thing about SciPy's Optimize that's kind of surprising, it's Newton, is that it's in pure Python. So it turns out that they do it in pure Python because the number of function evaluations is usually like dominating and it's small. I mean, it doesn't take very long. So it's actually in pure Python. And then if you implement it in Python, you'll get something. It turns out it's just about the same speed. Because I think the function evaluations just dominate. So that you do so much little work. But that said, if you're going to do a lot of Newton approximations to roots, doing it yourself with some Python implemented code is likely to be much better than calling SciPy's Newton. Because SciPy's Newton turns out to be in pure Python. So the main lesson is that you should, when possible, if you're really serious about using a function, you should figure out how it's implemented, even if it's in SciPy or anything else. Because it could be some really fast code, it could be a lot slower than what you could easily do. Or there could be a trick in there that you could combine with something you can do. Okay, so on Wednesday, Josh...
Bisection plus Newton.
Yeah.
You can bisect a little while and Newton.
Yep, exactly. And in fact, SciPy has, there's some wrappers like find root, which you give it an interval, it finds a root. This combines various techniques. So Sage has things like this. Just give it any function, do .find root. You don't have to even know about SciPy to use this. There's also like minimize and maximize and all these sorts of things. Josh Cantor is going to talk a lot on Wednesday about multidimensional optimization and root finding.